Hello there, and welcome to our unit on gases. In this unit, we're going to learn some more about how gases are unique and how we make measurements with them, and of course, how gases will react with each other and give quantities that we can predict. This is some dry ice that my son is playing with, and yeah, you can see by the look on his face, it's pretty awesome. So of course, the three states of matter that we bother much with in high school have to do with the strength of the bonds between the particles. And for solids, of course, that bond is very strong. For liquids, it's starting to be overcome by the heat, and you can see these particles can move. They're free to move around, and you can pass your hand through water, and that's because the bonds aren't as strong between the particles. And then with a gas, there's very little attraction between the particles, and they're free to move throughout any space that they might be found in, right? And they're all moving randomly in every direction. So the kinetic molecular theory is what we're going to use to explain many of the properties of gases that we're going to look at. Kinetic just means motion or movement. And so there's three different ways that particles can move. They, of course, can move from place to place. That's translational. If it was here and then it moved over to here, that's a translational type of movement. They can vibrate. So if there's bonds, of course, the bonds can vibrate up and down. You can think of the bonds between atoms in a molecule as kind of being like springs as well, and so they can vibrate back and forth along those axes as well. And so that's a form of movement. And then they can also rotate in place, right? If they can spin around, if they have a structure around which they can spin. So you got rotation, vibration, and translational motion. The temperature of a substance is based on the average of the translational movement, right? That place-to-place type movement. So a cold object will have particles in it that are translating or moving very slowly. They bump against each other, they bump back to where they were, and they vibrate back and forth. When you warm them up, they bump against each other a little harder, they spread out a little bit more, and that kinetic movement, that translational movement, becomes more random and violent, and eventually will cause these particles to separate. Now, the amount of energy that a particle might have is due to two things. One is the speed, right? The velocity of the particle moving from place to place. And the other is the mass. So both of those components go into the kinetic energy of a particle. And so the general relationship I'd like you to understand here that might help you later on as we're looking at different types of gases is the more mass of the gas, the slower it needs to move in order to have the same amount of kinetic energy. So if you have neon and helium at the same temperature, well, the helium atoms are moving a lot faster in order to have that same amount of kinetic energy. If this is much smaller, if the mass is much smaller, well, then the velocity or the speed has to be a lot higher. And this kinetic energy over here, if it's going to be the same, if they're at the same temperature, this one has a greater mass, which means the velocity will be lower. So since kinetic energy is related to the temperature of particles, it's important to be able to compare those temperatures accurately. The Celsius scale works really well for us here in Canada. It's based on setting 0 to the place where water freezes, and then 100 is where water boils. And so this is a pretty good scale for us. It's nice to know by looking at the temperature whether it's likely to be raining or snowing out. And so it's pretty useful that way. But it's not the most useful when it comes to other behavior of particles, and especially not with gases. So a second scale is what's used in science and chemistry called the Kelvin scale. And so the Kelvin scale uses the same increments, thankfully. 1 degree Celsius is the same as an increment on the Kelvin scale. It's just where you put 0. So 0 on the Kelvin scale is where particle motion stops. You can't get any colder, and so that's called absolute 0. Can't get any colder than that because the particles have stopped. And so in order to convert between the two of them, since the increments are the same, it's pretty easy to do so. 0 on the Celsius scale is 273 on the Kelvin scale, and 0 Kelvin is minus 273 degrees Celsius. So all you need to do is just add or subtract 273, and you got yourself the other scale. So 10 degrees Celsius, if 0 is 273, well, 10 degrees is going to be 283 not degrees, just Kelvin. And then 230 Kelvin, well, that's not quite 273. You got to add another 43 degrees to get to 0 Celsius, so that'd be minus 43 degrees Celsius. So the next variable or feature of gases that we're going to look at is the pressure that they exert. So gases exert pressure by the particles, the molecules, bumping up against surfaces that they come in contact with. And so the more bumping or the harder they hit those surfaces, the greater the pressure will be. So there's a whole bunch of different ways of measuring gas pressure. The original method used a dish of mercury. An Italian guy named Torricelli. He filled up a dish with mercury. I guess they didn't know how bad mercury was back then. So this dish full of mercury, and then he took a tube, like a glass tube, and filled it with mercury and turned it upside down in there. And so he had this tube that was filled with mercury, and it was turned upside down into a dish also filled with mercury. So mercury is a very dense liquid, obviously being a metal, and so it's going to have, you know, a pretty big force of gravity pulling it downwards. But what he found was that it only sank down a little ways. There'd be a little bit of a vacuum up here, and then it stopped. So that meant something else must be pushing the other way to balance that out, and that push the other way is the atmosphere. And so the atmosphere is all the gas that's all around us here. We're walking around on the surface of our planet. We've got this column of gas above us all the way to space that's constantly being pushed down around us due to gravity pulling it downwards. So that pressure pushing downwards here had to equal the pressure of the mercury that also wants to come down. So in order for this mercury to come down and out of this tube, it's going to have to push the surface of this mercury dish, the surface here, upwards. And so there's the tug of war, or the push of war right there. You got the atmosphere pushing down, and you've got this dish of mercury with the weight of this column trying to push upwards. And so once they balance out, you could use this as a way to measure atmospheric pressure. And what Torricelli found was that 760 millimeters was an average height of mercury that could be supported by the atmosphere. It didn't matter if you made the column longer, 760 millimeters of mercury is all that could be supported. Now, there are fluctuations. Of course, if you watch any weather station, you'll hear about what's happening to the pressure, and it often is an indicator of how the weather will change. And so this would fluctuate. If there was a low pressure system, that means that this arrow pushing down here would be smaller, and that would allow some more of this mercury to come down into the dish. And if there was a high pressure system, that means that the mercury in the dish would be pushed down further, and that would force the mercury back up into the tube. And so these fluctuations up and down here could be used to see changes in atmospheric pressure. So air pressure decreases as you go higher up in the atmosphere due to there being a shorter column of air above us that is pushing down on top of us. So if you go up on a mountain, you can also think of it in terms of like concentration. Up here the air isn't as tightly compressed, and then as you go down the mountain or get closer to like sea level, the concentration increases because it's all being squished by the air particles above. So a lot more air particles all bouncing around against you when you're down here closer to sea level than if you're up higher on top of a mountain. So atmospheric pressure or gas pressure can be measured in a variety of ways. This is a barometer that my dad has, and it's got two measurements on it. You can see kilopascals, which is like the standard SI unit, and the older, more traditional unit of inches of mercury, which is similar to the millimeters of mercury that we discussed with the original Torricelli barometer. Yeah, so there's a bunch of them here, and you can convert pretty easily in between them as long as you know the standard values. So atmospheres is a standard measurement of pressure. Like 1 atmosphere is like average pressure at sea level. And that's equivalent to 760 millimeters of mercury. Sometimes millimeter of mercury is called a torr, after the guy who invented it. And then there's kilopascals, which is the SI unit. And so 101.3 is the same as 1 atmosphere. And then there's pounds per square inch, which is another measurement of pressure, which would be like the weight of 14.7 pounds pushing down on 1 square inch of area. So converting is pretty easy. You can just do it like factor label method. So if you want the kilopascal pressure, so you want kilopascals, and you have 480 torr, you just use the relationship from these equivalences. So 760 torr is equal to 101.3 kilopascals. So you put 760 torr on the bottom, so it'll cancel out, and 101.3 kilopascals on the top. So the torrs cancel out and you end up with kilopascals. So let's see what that comes out to. 480 times 101.3 divided by 760 equals 63. That's like 64.0. Yeah, so 64 kilopascals. So lastly, now that we understand the measurements for temperature and pressure, we can have a look back at those conditions. 101.3 kilopascals, that's standard pressure, of our atmosphere here on planet Earth at sea level. And 273, that's the Kelvin measurement for 0 Celsius. And so those are the two standard conditions for STP, for which the volume of any gas is 22.4 liters. The standard ambient temperature and pressure, slightly different, 100 kilopascals, so a smidge less, and quite a bit warmer, 25 degrees warmer on either scale. 298 Kelvin is the measure there, and due to that extra warmth, the gas will occupy a little more space.